Okay, in this video, we are going to look at using naive-Bayes classifier for numerical data. But before that, we look at a measure called a Gini impurity index that will be very useful to identify the appropriate feature that can be used for classification. And this is very useful for the other modules as well that we'll see in this course. So I'll just introduce theory first and then go over a few examples that will make sure you understand how to compute Gini impurity index. Okay, so it's a measure of how, to what extent, so it's a quantitative measure that captures the extent to which a feature and its corresponding values are impure. So what I mean by pure or impure is this. If all the records for a feature of a particular value belong to the same class, then the feature value is said to be 100% pure, otherwise impure. So for example, let me see. So you look at here, Outlook, where its feature, Outlook is a feature and its values are overcast, rainy, and sunny. So there are 4 records with overcast as the value. And this data set has 2 classes, yes or no, to play tennis. And you see all the 4 overcast records belong to the class yes. There's no record that belongs to the class no. So we say the Outlook feature with overcast as its value is kind of pure, is 100% pure because all the 4 records, overcast records, belong to the same class. Whereas if you look at, for example, rainy or sunny, doesn't matter. You see Outlook with sunny, there are 5 records. Out of those 5 records, 2 belong to the class no and 3 belong to the class yes. So it's not a pure feature value pair. So there's some kind of impurity in it. Similarly, for example, if you look at temperature with hot as its value, there are 4 records with temperature hot, and 2 of them are no, and 2 of them are yes. This is actually the the maximum impurity you can have. Out of 4 records, you have 2 records belonging to one class, which is class no, and 2 records belonging to another class, class yes. That's the maximum impurity you can have. Whereas temperature with cool also has 4 records, where there's only 1 no and 3 yes. So the level of impurity here with temperature cool is less than the level of impurity in temperature hot. So you would like to identify those features whose values have as much, we can say, as less impurity as possible. Okay. So we'll still capture on base of impurity, but so we would like this to be as low as possible, as less impure as possible. So this is how we quantify the extent of impurity. For a feature x1 with a value a, we say there are k records for feature x1 with value a. So for example, for Outlook with say sunny, there are 5 records. So k is 5 in that case. And we identify the fraction of those k records that belong to each of the classes that are out there. So there are 2 classes in this example here. So 2 out of 5 sunny records belong to class no, and 3 out of 5 sunny records belong to class yes. So this PI in this formulation is basically the fraction of the k records of value x1 equals a belong to the class I. So like temperature equals, Outlook equals sunny, 2 over 5 fractions belong to class no, and 3 over 5 fraction belong to class yes. So we kind of square all those fractions, sum them up, and do a 1 minus. So that would get us the extent of impurity in the data set for this particular feature value pair. So let's do some examples and that will kind of reinforce this idea. So this is the tennis data set where we had 4 features: outlook, temperature, humidity, and windy. And the 2 classes are to play tennis yes or play tennis no. And let's look at Outlook in this slide here. So X1 is the Outlook feature, and we want to basically quantify the extent of impurity in this data set when we look at Outlook as a feature of interest. So the three values for Outlook are overcast, rainy, and sunny in this data set. And let us first focus on computing the Gini impurity index for each feature value pair, and then take a weighted average across all the values to get the Gini index for the particular feature itself. So of the four overcast records, all the four belong to class S, and 0 belong to class no. So the formula would be for Outlook with overcast is 1 minus. So 4 over 4. 4 out of the 4 overcast record belong to class S. So 4 over 4, that's one fraction, whole square, plus 0 over 4, that's the other fraction, whole square. Only two classes, so you have only two fractions. So you square them up and add those squares. So 1 minus of that is going to be 1 in this case, because 4 over 4 is 1, 1 square is 1, plus 0 squares. So this, everything inside the parentheses will add up to just 1. So 1 minus 1 equals 0. So when you get 0 as the Gini index, impurity index for overcast, so for a feature value pair, that's the best level of purity we can have. It's not impure at all. It's 100% pure. Okay. So let us look at for the other two values for this Outlook feature. So with sunny, you have 2 of the 5 no records and 3 out of 5 class yes. So it doesn't matter because it's addition. You can consider class yes or class no or class no and class yes either way. You're adding up the squares for the fractions. So 2 over 5 for no square plus 3 over 5 for yes square. Sum them up, and 1 minus of that is going to be 0.48. And then for rainy records, we can have 2 S, but 3 no's in this case. So 3 over 5 S, no, 3 over 5 no. So rainy out of 5, you have 3 no's and 2 S. So 3 over 5 no plus 2 over 5 S. So 3 over 5 square plus 2 over 5 square will again be 0.48. So as a weighted average, we can do a Gini index for Outlook for the feature as a whole. We'll take a weighted average. So 4 of the 14 records are for overcast, and its Gini impurity index is 0 for overcast value. Then 5 over 14 are for sunny, and 0.48 is its Gini index. And another 5 over 14 fraction is a weight for the rainy value, and its Gini impurity index is 0.48. So if you take a weighted average of this, that will get you 0.34. And the best way you can do this math here will be just say 4 times 0 plus 5 times 0.48 plus another 5 times 0.48 divided this by 14 will get you that Gini impurity index. Now we can actually do a comparison, which among these 4 features is less impure. And in the next module on decision trees, we'll be actually doing something like that to identify the feature that will be the least impure and use that as a basis for classification. So please make sure you understand how to do this, and it'll be very, very useful for this module as well as the next module. Okay. All right, so let us now look at temperature as a feature of interest, and its values are cool, hot, and mild. So of the 4 cool records, we have 1 no belonging to the class no, and the other 3 belong to the class yes. So it's going to be 1 over 4 belong to the class no square plus 3 over 4 belong to the class yes square. And 1 minus of that whole thing will be 0.375. And there are 4 hot records, 2 belong to no and 2 belong to S. So that will be 1 minus 2 over 4, you can say for no, that's square, plus 2 over 4 for class yes, that's square, and the math will give you 0.5. There are 6 mild records, 2 no's and 4 yes. So that will be 1 minus 2 of the 6 belong to class no, and 4 over 6 belong to class yes. Square each of these fractions, add them up, and 1 minus of that is going to be 0.444. So if you now look at the temperature feature as a whole, and we want to compute its Gini index, then 4 over 4, 4 of the 14 records basically have cool, and its Gini impurity index is 0.375. Another 4 over 14 for hot, and its Gini impurity index is 0.5. And 6 over 14 for mild, and its Gini impurity index is 0.444. And if you do the math, you get 0.44 as the Gini impurity index for temperature as a feature as a whole. So if you just compare temperature and outlook, it should be outlook, I'm sorry. You say outlook is less impure than temperature. So we would, between these two features, outlook and temperature, we would prefer to use outlook as the feature of interest that can be used for classification. So that's more, is less impure than temperature. So that's kind of how you compute the Gini impurity index. And so in the example that we just saw, we had only 2 classes. We can do it for multiple classes as well in a data set, if you have multiple classes in a data set. So let's say we look at this record where you have this data set where you have age and gender, and these are the 2 features, and favorite sport is a class. So the 3 classes. So you're basically in this data set trying to model what will be the favorite sport for people based on their age and gender. So we have 3 classes here: cricket, and then football and tennis. So if you try to decide between these 2 features, which is less impure, so let's do one for each feature. Let's start with gender. Its 2 values are male and female. So out of the 4 female records, we have 2 belonging to class cricket, 1 each to the class tennis and football. So the Gini impurity index for gender with female, F as the feature value. So it's 1 minus 2 over 4 for cricket, 2 of the 4 records for cricket, that was fraction square, plus 1 over 4 for tennis square, plus 1 over 4 for football square. And if you do the math, you get 0.625 as the Gini impurity index. Then you have 6 male records, and you have 2 each belonging to the class cricket, football, and tennis. So you'll have 2 over 6 for each class. So that's a fraction for each class. You square them up and add those squares, and 1 minus of that, sum of the squares of the fractions is 0.667. So if you now do Gini impurity index for gender as a whole, 4 of the 10 female records had an impurity index of 0.625, and 6 or 10 male records had 0.667, and the weighted average comes out to be 0.6502. So we would like it to be as close to 0 as possible, and at best it could go to 1. So it's more, it's larger in this case. So I wouldn't say this is a very pure pure feature. Let's try for age. With age as the feature, we have 2 values, old and young. So there are 7 records with old and 3 records with young. Out of the 7 old records, we have 2 belonging to cricket, 2 for football, and 3 for tennis. So the fractions are 2 over 7 for cricket square, plus 2 over 7 for football square, plus 3 over 7 for tennis square. And 1 minus of those sum of the square for the fractions will use 0.653. And then for the 3 young records, we have 2 for cricket and 1 for football, nothing for tennis. So it will be like 2 over 3 for cricket square, plus 1 over 3 for football square, plus actually you can say 0 over 3 for tennis, but since it is 0, I didn't show that here. So the math will give you 0.44 as the Gini impurity index score. So Gini impurity index for age as a whole will be 7 over 10 for female, old, times 0.653 plus 3 over 10 for young times 0.444, and that will give you 0.5903 as the Gini impurity index for based on age. So comparing the two impurity index values, relatively age is a better feature that can be used for classification than gender. It is less impure compared to gender. So that's how you kind of identify the feature that will be the least impure among the features out there and proceed with that for classification. And we'll come back to this also in the next module on decision trees in greater detail. So let's now look at what is the focus of this video, how to use naive-Bayes classifier for working with numerical data. Actually, here I show a data set where you have a mix of the features. We have two features, homeowner and marital status, that are more categorical in nature, and the annual income, which is more numerical in nature. So the idea behind this data set is to capture what kind of people are more likely to become a default borrower. So, and actually becoming a borrower as defaulted borrower is not a good thing. We would like to kind of do a prediction what kind of people based on these three features are more likely to become a defaulted borrower. So those people would never pay back the money they got. Okay, so or they borrow. So the three features are homeowner. So the values are yes or no. A person is either a homeowner or not. Marital status, you have three status: single, married, and divorced. And then you have annual income as a numerical feature, so it can take any value. So we already saw how to use how to do the what you call the Gini impurity index on categorical data in the previous two examples. So let us focus on the numerical data in this case. And for naive-Bayes, we actually don't need to do the Gini impurity index. If all your features are like the previous videos examples or categorical in nature, we don't need to do a Gini impurity index. We just go with determining the absolute probability and conditional probabilities and so on. So only if your data set has numerical data, that's when we need to use a Gini impurity index as a basis to basically transform this feature from numerical to a categorical data. And once we have things as categorical or everything as categorical like here, so basically the data set that we are given with, we have transformed into a categorical data set with annual income now having only like categorical values, high, low, and mod, or high and low. That's what we're going to decide whether we want 2 levels or 3 levels. We can then go ahead and with our usual approach of finding absolute probability and conditional probabilities and find the and do the appropriate prediction based on a Bayes classifier. So the way the way we are going to use Gini impurity index in this case is to decide for the feature with numerical values, in this case annual income, how many levels of classification or categories we need to have. Do we need to have 2 categories or 3 categories of income or 4? But we'll just try 2 and 3. Okay. So instead of levels, we can say 2 categories. That will be more appropriate, and 3 categories. Actually, categories levels mean the same, so it doesn't matter. Okay. But since we are calling things as categorical data, we'll use categories here. So that's what we're going to decide, whether we need to have 2 categories or 3 categories to represent or to capture this numerical data annual income. Now I have kind of have this type in my Excel file. So this is the raw data. No, this is the raw data with annual income. Now, if I had K along with the numbers, it was not sorting it properly. So I just said annual income comma K, and now I just have numbers. That's what it actually means, the salary on annual income. So if you sort this based on the annual income, this is the sorted order and the corresponding record information. Now, you can see there's an interesting trend here. People who had relatively low income among all the records were not default borrower, and then people who had relatively higher income are also not relatively default borrower. People who are kind of in the middle in their income or observed as default borrower. So it would clearly indicate 3 categories would be more appropriate. But let us just go with 2 categories first and see what we get as a Gini impurity index, and then we'll try 3 categories as well. So to get for 3, so for each case, we need to have a cutoff. So how do we classify these numbers to what category? So we need a range of income levels for each category. So if you go with 2 categories, then we'll go with the kind of the middle value. So this is, say, record number 5, and there you have 90K as income. So we can say anything less than or equal to 90K will be called as low income category, and anything greater than 90K will be called as high income category. And accordingly, I can classify categorize the records like this. So 125K will belong to high, 100K will be high, 70K will be low, 120 will be high, 95 will be head because you want less than or equal to 90 as low, and 60 will be low, 220 will be high, 85 will be low, 75 low, 90 low. Okay, less than or equal to 90K. So now if you try to you compute the Gini impurity index for this feature with annual income as a feature with values low and high as its values, we have 5 low records and 5 high records. And out of this 5 low, if you now look at the class for the defaulted borrower, out of the 5 low, we have 3 belonging to class no. If you look at this, 1 no, then there's another no here, there's another no here. So 3 belonging to class no and 2 belonging to class yes of the 5 low records. Similarly, of the 5 high records, 4 belong to class no in this case and 1 belong to class yes. So now we have a setup to calculate the Gini impurity index. So the Gini impurity index for annual income here, since it's one feature, I don't indicate annual income everywhere. I just say indicate the values of that feature. We are interested in annual income as a feature here. Let me kind of make like that. So with low, it's going to be 3 over 5 belonging to class yes, class no, and 2 over 5 belonging to class yes. These are the 2 fractions. So we square them up, add them, and 1 minus of that square, sum of the squares of the fractions, so 0.48. Now with Gini with high, you have 4 over 5 fraction for class no, that's square, plus 1 over 5 fraction for class yes, that's square, and 1 minus of that is going to be 0.32. So the overall Gini score for annual income is going to be 5 over 10 fraction for low, and the Gini score for that is 0.48, and 5 over 10 fraction for class yes, for high, and for that you have 0.32 as the Gini score. So the overall weighted average is 0.40 as the Gini impurity index for annual income with 2 categories, low and high, by using 90K as the cutoff for low, and anything above 90K is the high. So now let us go with 3 categories. And if you look at the data set here, we can say, so 75 is no, 85 is yes. So we can put 80 as a cutoff. So anything less than 80K will be low, and anything 80 to 100K will be moderate, and greater than 100 will be high. And it's kind of subjective. If you look at here, you could try with 80 to less than 100 as moderate, and greater than or equal to 100 as no. That will make it actually very pure. Okay, but to have some level of impurity, I made 80 to 100 as moderate. So it's up to you. Either way is fine. Okay. So we'll go with 80 to 100 as moderate, and anything above 100 only as high. So based on that, we have, say, 3 low records And the Excel file itself tells us that all the three belong to class no, so none of them belong to class yes. So 3 no and 0 yes. And of the 4 moderate records, because I am going with 100 inclusive as moderate, I'll have 1 no and 3 yes. So this one no here for 100K and 3 yes. And then greater than 100K, I have 3 no's. Okay. So the Gini input index for each of these feature values for low is going to be 3 over 3 corresponding to class no, the fraction, plus 0 over 3 fraction for class yes, the squares. So it's going to be 1 minus this 1, so that's 0. So it's very pure. And for moderate, you have 1 over 4 fraction for class no, and 3 over 4 fraction for class yes. So if you do the math, it's 0.375. For high, you have all the 3 belonging to class no. So it's 3 over 3 square plus 0 over 3 square. So it's going to be 0 again. So the overall Gini score with annual income for 3 categories is going to be 3 over 10, which is for low, times 0, plus 4 over 10 for moderate times 0.375, plus 3 over 10 for high times 0.0. So the weighted average is 0.15. So we'll go with 3 categories of classification for the annual income feature, as it incurs a relatively lower overall Gini score compared to using 2 categories. So once we do that, we can transform this annual income feature to a categorical feature instead of a numerical feature, and that's how we can do that. So anything above 100K will be called high, anything from 80 to 100 will be called moderate, anything less than 80 is called low. You can redo this as a practice. You can say anything 80 to less than 100K as moderate, and anything greater than equal to 100K as high. So I leave it as an exercise and see what you get as the probabilities. Okay. So we are now to our kind of standard way of looking at data sets for naive-Bayes classifier, where all the features have categorical data. So let's do one thing at a time. So this is what I have here. Okay, so we can redo this. Okay, let me make sure I have the same classification: high, moderate, low, high, moderate, low, high, moderate, low, moderate, low, high, moderate, low. Very good. All right. So save this first. All right, so we'll start with homeowner as a feature. And let us find the conditional probabilities. So for that, we'll sort by homeowner and then by defaulted borrower. Okay, so we see that we have no and yes as in 2 values. And there are 7 records with no and 3 with yes. So the absolute probability is going to be 7 over 10 and 3 over 10. So now we go to the conditional probability. So you have again no and yes as a 2 classes. Yes, restricted classes, yes, okay. So out of the 7 no records, we have 4 class no and 3 class yes. So 4/7 for class no and 3/7 for class yes. Then out of the 3 yes records, all belong to class no. So it's going to be 3/3 for class no and 0/3 for class yes. So that's the conditional probability for homeowner. So now we'll go to marital status. If you sort this based on marital status, we get 3 classes again. So divorce, married, and single. So 2 belong to divorce, 4 for married, and 4 for single. So it's going to be, so the absolute probabilities, let's put this here. So 2/10 belong to divorce, 4/10 belong to married, and 4/10 belong to single. And out of the 2 divorce classes, 1 belong to class no and 1 belong to class yes. So that's going to be 1/2 for no, 1/2 for yes. Of the 4 married, all the 4 belong to class no. That's 4/4 for no and 0/4 for yes. For single, 2 belong to class no and 2 belong to class yes. So it's going to be 2/4 for no and 2/4 for yes. All right, so that's for marital status. So now we'll do for annual income. So we have low, moderate, and high, we know that. And let's sort based on that. So we have 3 lows, 4 moderate, and 3 highs. Okay. So that will be 3/10, 4/10, and 3/10. Okay. So of the 3 lows, everything is in class no. So 3/3 and it is 0/3. Similarly, for the 3 highs, everything in class no. So 3/3 and 0/3. And for moderate, 1 no and 3 yes. So 1/4 and 3/4 for moderate. So that's the annual income. So now we are ready to do some testing. So let's find a test case. The test case is this. Home owner equals yes, marital status is divorce, and annual income falls in the moderate category, 80K to 100K. So based on the numbers, we have to decide the category for annual income. So provided we have done that, now we are ready to do the testing. So we want to find what is the probability that someone will be a defaulted borrower equals yes, given the test case, and then we have to find the probability for no. So let's do that. So this is going to be the probability that for the test case, given the defaulted borrower, will say default borrower equal to yes. Given that, what's the probability for the test case values to be observed times probability for default borrower to be yes without any condition divided by the probability of the test case. So we have these 3 feature values. So probability for, let's see, we can combine that like this. Given these for defaulted borrower equals yes times this as it is times this divided by probability of this whole thing here for this test case. Okay, so then it's going to be, let's use this table that we did. So default borrower, yes. Homeowner is yes. That's going to be 0. So right away we can know that this is going to be 0 overall. Marital status is divorced. Homeowner is, so defaulted borrower is yes. That's going to be 0.5. And income is moderate. Default borrower is yes. That's going to be 0.75 times. How many default borrowers are there? Overall, you have 3 default borrowers. So that's the unconditional probability. So the last case where probability of default borrower is yes, this term is going to be 3 over 10. 3 of the 10 records had default borrower as yes, divided by the absolute probabilities for each feature value. Homeowner equals yes, we have 0.3 times. Marital status is divorced, we have 0.2 as a probability, and income is moderate, we have 0.4 as a probability. But since we have a 0 here in the numerator, the whole thing will evaluate to 0. So that means given this test case, a person is not going to be a defaulted borrower because the probability of observing a defaulted borrower for this test case as yes is 0. The reason is because if somebody is a homeowner, that person has not become a defaulted borrower. So if homeowner is yes, there's no defaulted borrower. That's what we have in the data set. Okay. So let's redo this for no and see what probability we get. So this is going to be a 0 here and no here. And we know that as it said, as a trick, we can do 1 minus of these on the top for no. There are only 2 classes. If you have 3 classes with more than 2, you don't do that 1 minus. If there are 2 classes, just do a 1 minus. That's more easier. Or you can look at the table just to make sure you don't do any mistake. If there are more than 2 classes, make sure you look at the table. So for default borrower is no and homeowner is yes, the probability is a 1. So somebody who is not a, somebody is still a homeowner, yes, that person is not a defaulted borrower, guaranteed. So someone homeowner equals yes, it's not a defaulted borrower. Defaulted borrower is no. That's what this means. And marital status is divorced and defaulted borrower is no, is 0.5 is the probability. That's 1 minus 0.5. And then income is moderate and defaulted borrower is no, that is 0.25, which is 1 minus of 0.75 will be the 0.25. And then there are 7 records with defaulted borrower status as no. And the denominator is going to be the same. It's the same test case. So if we do the math for this, it's going to be 1 times 0.5 times 0.25 times 7 divided by 10 divided by 0.3 divided by 0.2 divided by 0.4. It's going to be 3.6458. So as I said, for conditional probabilities, you could get the probability value to be greater than 1. So it's obviously greater than 0. So we'll say for the given test case, the person is going to be not a defaulted borrower because the probability of observing for this given test case, the probability for the person to be defaulted borrower equals no in that class is 3.6458, and defaulted borrower equals yes is going to be 0. That's the probability. So we'll say the person is not going to be a defaulted borrower with this given test case. So that we finish this module.